Hello, welcome back. This is episode 3 of solving some problems of Rosetta code in Mathematica. So here's the rosettacode.org page, and here is the special page where they list all the tasks that are not implemented in Mathematica. And so there's our, let's say, final tasks, but there's also tasks that are still in draft. They also need implementations. So I selected a few of them. So here is the first one that I thought looked interesting, at least by the name. So we're looking here at a positive integer n is an arithmetic number if the average of its positive divisors is also an integer. Clearly all odd primes p must be arithmetic, or arithmetic, if you're from the US, numbers, because their only divisor are 1 and p, whose sum is even, and hence their average must be an integer. Having the prime number 2 is not an arithmetic number because it divides 1.5. Okay, 13 is an arithmetic number because 7 divisors are r. Their average is 9, which is an integer. So we can do this. So this is my let me just open a new notebook. And well, let's save this notebook just in case that we screw up halfway and we lose all the code. Alright, so we want to have arithmetic number q, and the input is some integer. So we can get the divisors of n. Oh, let's plug in the example. 30 was the example. So this gives us all the divisors. But I know there is also divisor sum, which might be better in this case. Resembles always divisor sigma even. Divide sigma is the sum. Yeah, let's do that. Wait. As the opposite. But then I don't know the number. Okay, I think I will just have to do, because otherwise I lose the number. The length of this list. So let's call this divs. And then we ask the mean of divs, and then we ask integer if this is an integer. Well, we can make this a lot shorter just by doing this actually. And so the first 100 arithmetic numbers. So if we do not wanna put an upper bound in there, what we can do is this: if I append to an, comma I, and then if length an is bigger than 100, then break. And then once it's done, show an. So let's see, 149. So I think this is all correct. It looks pretty promising. The x arithmetic number where x equals 1,000 and 10,000. So this is the 1,000th. 1361. So we need to find, okay, this will be very similar code a few times, but I guess that's fine. And now we take the 1,000, and then what we show here in the end is the length of this thing and the last of the end. So this basically gives us that the 1,000 is 3061, So let me see, what is this 782? Number of composite. Let me think what this means. How many of these are composite? Okay. Well, what we can do is how many there are prime. So cancel it. 783, was that the 782? That is surprising. Does this work? Does not. So not does not map automatically. So why is it 783? Might be a definition issue with if one is a prime or not. One should not be a prime. 782. What does this guy have? Maybe up to and not up to and including. So let's say the last of an. Is that prime q? Yeah, so that wouldn't contribute. How many of the first x arithmetic numbers are composite? So let's see what other people return. So do I make a mistake or do they make a mistake? Maybe. How long is an? 1000, yes. I'm slightly confused now. Why do I have one more than all the others? Is very strange. So let's see if I mistake something. Is an Arabic number because it's note that technically a Arabic number 1 is neither prime nor composite. Okay, so maybe this is the issue. Is there a composite key actually? There might be. Maybe it is just this little detail. Yes, that 1 is indeed neither prime nor composite. Okay, I didn't. So prime q is not the same as not of prime q, let's say. So x equals 1000, and then 10,000 goes stretch. Carry out the same action as in 2 and 3, but for 100,000. Let's see how long that takes. I think this. Let's see. Yeah, that should be reasonably quick. So to help myself, I can show how many I have up to now. Sorry, 100,000. I also want 1,000,000. So let's see, how many do I need? 100,000, which is the second thing. Oh, here we have 100,000. Then, well, let's also go for the million. Let's see if those are. Is this correct? And then, well, so some people output it as a little bit of text. Yeah, I don't know what. Maybe I can first change that a bit. Let's call this result A1. Let's call this A2. Let's call this A3. Let's call this A4. And then we do A1, A2, A3, A4. Well, let's make this short for now so we can quickly test it out. And then we can turn this into a table. Is that the right order? Ah, yeah, because there's now low. And then we say table headings. I think I can do something like this. Yes, so this will be X in series, composite, like this solution in Julia. So this might be the easiest. Then we go back to our higher limits and we run this. So let's edit this solution for Pascal. We dump in our header there. Walk away. So our code has a lot of repetition, but well, that is completely fine, of course. Oh, I don't like this here. And then the output would be in this. I think what I can do is do plain text. Ooh, that has no spaces. Maybe the other one is better. Okay, I will manually remove those backslashes. It's not too bad. So now we have to wait a little bit. So the higher the numbers you go, of course, the longer it takes to compute the divisors. Well, calculating the mean and the integer is very quick, but calculating the number of the divisors, let's say in general, takes longer and longer as the numbers go up. I'm not sure if I have patience for this, or will I just stop at 100,000. Let's stop at 100,000. Someone else can run also a million. I mean, it's just waiting a few more minutes, but well, I don't have the patience here. So let's copy this. Here we go. Let's save this page. Let's just double check. Yeah, looks all good. Right. So let's make a new notebook. Oh, I can also maybe enhance it a bit so you see it a little bit better. Rosetta, Cullen, Woodall numbers. All right, a Cullen number is a number of the form n times 2 to the power n plus 1, where n is a natural number. A Woodall number is very similar. It's n times 2 to the power n minus 1. So for each n, the associated Cullen and Woodall number differ by 2. Yeah. Woodall numbers are sometimes referred to as a result, blah blah, whatever. Cullen primes are Cullen numbers that are prime. Similarly, Woodall primes are Woodall. Okay. It is common to list the Cullen and Woodall primes by the value of n rather than the value, the full evaluated expression. They tend to get very large very quickly, well, exponentially, or more than exponentially. For example, the third Cullen prime number n and n equals 4,713, so 2 to the power 4,713, which has 1,423 digits. Write procedures to find Cullen numbers and Woodall numbers. Well, that is not so hard. So n to the power n plus 1, and we have Woodall number so that is very easy. Use these procedures to find the show here on the first 20 of each. Actually, I can also do this at attributes. I have to symbol. So I think I can do this and say listable. Oh. And now I can just say range of 20. Here we go. And Woodall. So they differ by 2. Okay, great. So is that, yeah, that is correct. Okay. And then find and show the first 5 Cullen primes in terms of n. Okay, let's make again an infinite loop. Let's call this Cullen primes. If prime q Cullen I, well, I could have used n, but well, that's okay. Then append to CPS I, and if length CPS is 5, then break. And let's have a dynamic of this. So I don't know what those primes should be. So a lot of people don't solve for the primes. I think these are. Okay, so this is what we found. And then, what was the other one? 12 Woodall. Okay. It's called Tilson. Well, we can do. Well, let's be consistent and call them WPS. right, let's, oh, that is very, very quick. Why is this so much quicker? Huh. That is, maybe they are in such a form that the prime checking is much faster. I don't know. So let's put all this code in one little brackety thingy. Let's save this notebook, let's run it one time. And then, well, I can copy this. Well, first I have to find the, so this will be above Perl. So let's copy the header here. Let's copy this code here. So I'll remove the print temporary, that's just for me more than that it is part of the solution. And then, well, we can copy these. We want to remove the enters, why not? Here we go. Save it, and that is good. All right, let's make a new notebook. And let's call it Rosetta equal prime composite sums. Suppose we have a sequence of prime sums where each term P, capital Pn, is the sum of the first n primes. So P equals r. Okay, further, suppose we have a sequence of composite sums where each term Cm is the sum of the first m composites. Okay. So what do we need to do? Notice that the third term of P, P3, is 10, is equal to the second term, C210. Find and display the indices nm and value of at least the first 6 terms of the sequence of numbers that are both the sum of the first n primes. Okay, let me see what they do mean. All right, let's get some primes. So I have to find the first 6. Okay, let's first get some primes. So let's do upper bound. Upper bound is 10 to the power 5, let's say, or 10 to the 4, just for testing. And then we can find the primes up to that. So these are all the primes up to 10,000. And then composites. Yeah, what we can do is we do the complement of range UB, starting at 2, comma PS. So these are all the composites. And now we can do the cumulative primes. And, well, we can use accumulate for that, PS. And you can do cumulative composites. So now the question is, what is the intersection of these, right? So yeah, basically that is it. I just need to make a little bit higher upper bound, but I guess I can push it a little bit. Let me just make sure that my memory is not being loaded full with all kinds of junk. Okay, let's do 100 million. Of course, people can do a billion or even bigger, but here we go. And now, well, basically we have to find the position. Okay, let's call this the indices. So what we can do, first position. Let's see, how does it list? Expression pattern. So CPS, comma 2, comma CCS, and slash indices. So this will look for these numbers, the indices of those. Not sure why this takes so long. Shouldn't this be roughly instantaneous? If I look for 10. Okay, but let's look for the big number. Okay, let's look for the biggest number. 94 million entries. Okay. Okay, maybe I'm just too maybe I just need a little bit more patience. I mean, we are talking about pretty massive numbers, right? So basically this is the first column. This should be the second column. This should be the third column. So okay. So here we go. And then okay, I have to do some trickery to join these. And here I want the indices prepend. So now I basically get this table here. So give it a nice column names. So this is the sum, this is the prime index, and this is the composite index. Do I want to align it to the right? Not sure if that will make table alignments. Guess I can just do right. Just right. Here we go. Yes. So now it's very similar to this one. All right. Oh, there's not so many solutions here. Only 13. We can add the 14th. Well, and 15th, because I do. I mean, you see here I put both headers because in many of the solutions, many of the tasks, the solutions for Mathematica and Woven language will be identical. So it's only when you have to build like a user interface or things like that, that potentially they would be different. And well, so most of the time, it does not copy so nicely. Okay, this one, by the way, we want to suppress and copy as plain text, because this is not so nice to read. So this one I don't output. This one, actually I also don't want to output that one. I just want to output the table. So here I will add some semicolons, and well, let's also remove this. And yeah, that looks good. Let's say save. Okay, that doesn't output so nicely. So I'll do a manual fix, let's say. So are these tabs? Yes. So in Mathematica it will show up, properly. But the copy paste is not so good. No. Well, because probably the size of a tab is probably different on different systems. Let's see if it's correct now. Yeah. All right. So what does it do here? Does it also select some upper bound? It just says that first. Oh, that's similar. All right. This one is also solved. Let's now look at Erdös-Selfridge categorization of primes. A prime P is in category 1 if the prime factors of P plus 1 are 2 and or 3. P is in the category 2 if all the prime factors, all of them, okay, I guess we should also all the prime factors are 2 and 3. P is in the category 2 if all the prime factors are in category 1. P is in category G if all the... Okay. Let's see how to do this. Let's save this name. The task is first with the first 200 primes. So these are the primes, first 200 of them. And now we have to see in which category they are. Right, so we select from PS where the prime factors, let's make a little function here. Let's say special prime factors. Factor integer of n plus 1. It's all n plus 1, right? Yes. Maybe do p in this case. And then I don't care about the multiplicities. Select from special prime equal to how do I do this? Equals 2. Maybe it's 2, 3, or 2 and 3. I can also do this, maybe. Complement, 2, 3 equals empty list. So let's call this category 1. P is in category 2 if all the prime factors of people are in category 1. So category 2. are in C1. I guess we have to remove C1 from here. 13, 19, 21, 12, 23. Okay. So I like that we can use basically the same piece of code a few times. Ah, wait, this is C2. Oh. Oh. That is not what I would expect. Ah. So we just increment all these indices a bit more. Now we also include C3. So how long is PS now? Oh, it's only 21 left. Okay, maybe I can optimize this a bit. C0 is 2.3. Well, let's call it CS. Do. From n to 1 to infinity. If length PS is bigger than 0, then otherwise break. New C equals this. We can use catenate of CS. Here we go. And then boom. And then what we do is append of CS of new C. Is this all correct now? Let's monitor this by monitoring PS, CS, and N. Ooh, this should be append too. Very important. Da-da-da-dum. So what do I have to do? Just wondering, why is there an empty list? Ah, this is in this thing. Here we go. So now, yeah, I can show this in a table form where the table headings are, I think just automatic. Maybe this is not what I wanted. Maybe I have to do, say, table depth 1. Table headings. Maybe just automatic. That works. Now for the first million primes, right? Yes. So this will be the first million primes. Yeah, I have no idea how long this will take, but I guess pretty fast, I hope. Oh, I think my kernel crashed. Well, that's not so nice. So let's split this here. So it should be 11. I would have to go through a million times doing the vectorization, so that's probably why it takes a while. And I'm not sure if this is the, let's say, the fastest way of implementing this. Yeah, I have no idea. Wait, is the million a stretch goal? Oh no. Why does it take so long? That is a very good question, which I'm not sure why. Yeah, maybe I just want to calculate these special prime factors once. That will save a lot of time, huh? Okay, stop the code. So, so maybe we can do this. So select from PS, where last of it, and then new C equals new C, all, 1. I think complement. Let's see. This is new C, by the way. Okay, let's test this out anyhow on much smaller numbers. Let's think about this. So I want to carry this over so I don't have to calculate this every freaking time. So well, this will... It's also a bit idiotic to calculate this every single time. Catenated CS equals so maybe that also speeds things up a bit, but then gives this also do this. First do the complementary, yeah, maybe this is better. So CS. Okay, how much is this? How much was this? 200. Let's do that as an example. Okay, that is pretty fast. Let's see. So why is this so slow? I'm wondering. Is it the complement that slows everything down so much? Because I do a complement for each PS. I'm not sure if we can do this in Mathematica in a fast manner. I would guess that yeah, I'm thinking if I have all these prime factors here and they find a new set of C's, what I can do is just once I have this, in PS remove all of these that are there, so just annihilate those numbers and then just look for empty lists in PS. Maybe that is a lot faster. Okay, let me just copy this code. So here we have the calculated CS. Not sure if I need that anymore. Let's say the new C's were the last of the CS. Okay. Now in PS all comma 2 replace what happens with this? 2 with nothing. Empty list, okay. Alternatives. How does it work again? Add new CS. Becoming nothing. Let's see if I can do that. Now last. We can do, well, let's see, I want to do last, then I'm going to take the line, it should be equal to 0. That should still work. That should still work. Yes, let's see if this works. What takes so long then? Print 1. Let's do this, and 1, and 2, and 3, and 4, 5, 6, 7. Why would that take so long? I mean, this is what Mathematica should be good at. To do those replacements very efficiently. So I wanna delete elements, maybe. It's a new function. I think it only works at level 1. So replacement. Because CS. Yeah, it takes 40 seconds. That's really long actually. Save this for temporarily. Thinking of how to optimize basically this step. So now I use alternatives. Ooh, there is this command which speeds up the rules, and it's called deploy or something. No, not deploy. Deployed. No. This should be in rule, I guess. Look up. No. Set key. Has a bit of an obscure name. Dispatch. That's what I was looking for. Oh, I can also try that. So this was 40 seconds. But if I do, let's say, thread, new CS, nothing. Does that work? Yes. Is that faster or is that slower? I don't know. And then the second question is this even faster? This one does not look faster. So I don't know if dispatch works with alternatives. Dun, 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 dun. Okay, this is slower. Oh, why is this so much faster? Well, it's good to know this that dispatch can make a big difference. Okay, remember guys, use dispatch when you have a big list of things to replace, because it can be a very big difference. Okay, there's still 100,000, so now we do the million. But now I at least have a little bit of faith that this thing will be done in some reasonable time frame. So, okay, so these are all the CS. First, last count. Okay. First, last count. And then we do this in a table form. Here we go. Table headings. I guess we want automatic here, and here we want category. First, I mean the category will be first, last, how do we call this, amount or length, count? That's a count. And I think this looks very much, I think it was table alignment, table alignment, right. So at least in Mathematica it looks nice. So we'll throw away this code. I mean, I don't know. I guess for this is fine. Do I want to output this in a different manner? Maybe I do want to do that. So we can use multi-column like they did there of CSI, and then what is the notation again? Rows, columns. Rows, so automatic, comma 10, and then print it. And then before that print category I. It's I minus 1 in this case. Oh, this may be a bit inconsistent. Skip the first one. Here we go. Oh, shit. I had overwritten the CS here, so I have to recalculate it. But it goes pretty quick now with this dispatch thingy. Yes, so. Alright, that was much harder than I thought it would be. Because of these replacements rules that were much trickier than I thought to get them performant enough. Of course we can always do this, but wait a long time. But we don't like to wait a long time. So let's see if this copies nicely. This copies actually pretty nicely. There are some extra new lines, but we can kill those. So this was how it would show up, let's say, in Mathematica. And then this table we can again copy as plain text. So this null wouldn't show up. Here we go. Save page. That looks pretty sweet. Alright, let's do one more. So I had a few more, but well, it's almost an hour now, so let's do this last one. Given a left to right ordered collection of E bits, left to right ordered, okay. I'm not sure what that really means. Where E is between 1 and 10k, and the 0 more integer n. Output the result of setting the n bits to the right of any set bit in B, if those bits are present in B and therefore also preserving the width E. So n equals 2, width equals 4, so we have the input. So these are bits. And, so we have here 1 bit, so then these 2 become 1. 1 bit, and these 2 become 1. So here, so we have a big number, and then we find the ones, and then these become 1. So this can be done with bit shifting very efficiently. Do I want to use bit shifting, or do I want to use just looking for bits and etc. So let's see how ren does this. Set right bits. Okay. Let's say that we start with some bits. B. I mean, I can do it as strings, or I can do it as numbers. I'm not sure what is the best approach, but set right bits, where B is a string, and what was n equals the, I don't know what we call it. N is an integer, I don't know what you call it. So first we ask for the characters of B, then we find the position of ones. Okay, let's do 2. So these are the positions. So I guess we want to do outer. Function is going to be plus positions, comma 1, 2. So we flatten all that. We say the union, so if there's any duplicates, and then so these are the process again. Chars. So this is chars. Boom. And then what we're gonna do, we can do replace part. I think is the replace part. Replace the part. Yes. So we do have to add some extra braces, but we set it to 1, string 1. and then we join this all again. So let me uncomment this so we can compare. Yes, so I have to, so if it doesn't exist, it doesn't matter, I guess. Let's see what happens if I do 1, 2, 3, 4, 5, and I say the 10th position, turn it into a 7. That is fully ignored. That is beautiful. Rosetta. Some examples. Tasks. Implement a routine. Use it to show here the same for the input examples above. Print to show the output line. Yeah, okay. I'm not sure if I have to do all the examples. I think some of them are a bit silly, to be honest. So especially the simpler ones. Oh, the 0 case. Maybe that does that work? Maybe the outer will get. Okay. Maybe I should make here a show thing, and then this shows the original, and the this one in a column, such that in simplifies things a bit. Zero, zero, 1, 0, all zeros, and then n equals 0. One, two, three. 1, 2, 3. I think that works pretty well. Was a slight mistake. Yeah, that looks pretty good. Let's add this now here. This will be the last one because we've been more than an hour. I hope I can copy this as plain text. Ooh. Okay, I have to do them one by one for some reason. And the last one is pretty sweet. process this. Boom. Okay, code is not so pretty, but let me add some, just indent this a bit, make it a little bit nicer. Oh, I could have checked the minor edit. Well, that is all fine. All right. Let's go now to the Mathematica page and see how many there are implemented. So it keeps a track here. So we have now 1146, including the ones that we implemented just now. So this problem was called set. Let's look for a right maybe. Yeah, so set also just the one that is automatically also in here now, so it calculates it every time we do this. Right, so 1146. And in the non-implemented list, well, I don't know the number here, but I can find out. I made these functions, so Mathematica not done. Let's see, so 133 are now left for Mathematica left to do. So this function crawls this page and takes these entries, and if I think, oh, this is something that I can easily do, then I can click on it and it will open that page basically. Alright, hope you liked this one, and see you in the next episode where I will solve some more of these lists. See you around.